Hi, in this video we're going to discuss polynomial interpolation. Now, after what we saw in the introduction video, the name says it all. We want to combine interpolation as the approximation criterion with polynomials as the approximation type. As we know, the input are n plus 1 points xi together with their images f xi for I going from 0 to n. One final remark, the polynomial px can be expressed as a0 plus a1x plus a2x squared plus dots anxn. Note please how a polynomial of degree n has n plus 1 coefficients, including the independent term, and this is precisely why we start counting coefficients and points for I equal 0, not I equal 1. The fundamental theorem of algebra establishes the existence and uniqueness of the interpolating polynomial. It goes like this. Let xi f xi with I from 0 to n be a set of n plus 1 points with different abscissa. This is an important condition. So xi is different from xj for I different from j. Then, under these conditions, there exists, so existence, a unique, so uniqueness, polynomial Pn of degree n or less than n that is interpolating. The proof is rather simple and constructive, meaning that we are not only going to show that the polynomial exists and is unique, but also how to obtain it. To do that, we simply take the expression of the polynomial and replace it into the interpolating condition. By doing so, we obtain this linear system of n plus 1 equations in n plus 1 unknowns. Indeed, we have here n plus 1 equations because a goes from 0 to n, with n plus 1 unknowns, the coefficients aj, with j going from 0 to n. Now, if we write this system of equations in matrix form, we can see how the first column of the matrix contains 1s, the second column contains the xi, the third column the x squared, and so on. Unknowns are the coefficients of the polynomial to be determined, and the right-hand side vector contains the images f xi. Going back to the matrix, this is the so-called van der Monde matrix, and a well-known property of this van der Monde matrix is that it can be expressed as the product of these differences between the abscissas xi. So since we assumed in the hypothesis of the theorem that all these abscissas are different, all these are different from 0, so that the determinant is different from 0. In other words, the system is the matrix is regular, the linear system is compatible determinate, so we indeed have a unique solution. The only drawback of the approach just presented is that the van der Monde matrix is ill-conditioned. A possible solution to this problem is to change the polynomial basis. Rather than expressing the polynomial in the natural basis of monomials 1, x, x squared, and so on, we will use a different basis to obtain, of course, the same polynomial, because we just saw that it is unique, but expressed in a different basis, and leading to a well-conditioned matrix. One approach along this line is what is known as Lagrange interpolation. So what we do in Lagrange interpolation is express the interpolating polynomial as a linear combination of polynomials Lj of x, those are the Lagrange polynomials to be determined. Then, when we again impose the interpolating condition, we end up with a linear system of equations that can be expressed in matrix form. So what we see is that the matrix contains the Lagrange polynomials evaluated at the basis points. Well, now Lagrange polynomials are defined in such a way that the system matrix is the identity. In other words, we require Lj of xi to be 1 if I equal j, that is, once in the main diagonal of the matrix, and we require Lj of xi to be 0 if I is different from j, that is, zeros in the off-diagonal entries of the matrix. This condition, this Kronecker delta condition, can be verified if Lagrange polynomials are defined in this manner. In the numerator, we have the product of x minus x1 dot x minus xi minus 1. Please note here that we skip x minus xi. The next term is x minus xi plus 1 dot x minus xn. With this polynomial of degree n in the numerator, we ensure that Lj of xi is 0 for I different from j. In the denominator, we simply put a scaling factor, which is the polynomial on top evaluated at xi. This makes sure of the 1 in the diagonal of the matrix. Of course, since the system matrix is the identity, the unknowns IA are directly the right-hand side entries fxi, and the interpolating polynomial can be expressed simply as the linear combination of the Lagrange polynomials with the images themselves. What is the approximation error of polynomial interpolation? What is the difference between f and the interpolating polynomial? Of course, by construction, this difference is 0 in the basis points. But what about in a point x different from a basis point? Well, this is given by this theorem, which goes as follows. Okay, let f be a smooth function, more specifically a function of class Cn plus 1, and let Pn be an interpolating polynomial that verifies our usual interpolating condition. Let Rn be the approximation error. In other words, f can be expressed as Pn plus r. Well, then, according to this theorem, this approximation error, called Lagrange remainder, can be expressed in this form. Let's explore the structure of this formula. On the one hand, we have here Lx. Lx is a polynomial of degree n plus 1 with all the basis points x0, x1, dots, xn without skipping any point. In other words, Lx takes care of ensuring that Rn in xi equal 0. And then we have here the derivative of order n plus 1 of f evaluated at some point mu that contains all the basis points and the point x where we are evaluating the remainder over n plus 1 factorial. To finish, we are going to discuss the so-called Runge's phenomenon. What we do is take this rational function and approximate it by means of interpolating polynomials of different degree with equispaced basis points. So the rational Runge's function is shown in red. The blue line represents a polynomial of degree 5 that coincides with the red curve in this 1, 2, 3, 4, 5, and 6 points. In green, we show a polynomial of degree 9 coinciding with the red line in this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. And what we see is the following. The approximation gets better in the top of the hat, but we have increasing oscillations in the wing. And this behavior only gets worse as the degree of the polynomial increases. In other words, polynomial interpolation with a polynomial of high degree may be dangerous in some applications because polynomials of a high degree oscillate a lot. We'll see in future videos how to address this situation.